the shape of a flower to the numbers on a clock. Everywhere you look, you will be able to find some sort of pattern, whether man-made or natural. However, patterns can be much more than a set of shapes. In mathematics, patterns are an essential and central part. Welcome to the first episode of the Equationators math class. This is student teacher Kat. Today, we are going to talk about the first MELCs-based module of mathematics in grade 10, generating patterns. Are you ready? Halina't MATHtuto tayo. Hey there! You might be wondering why I am staring at my grandma's calendar. With these encircled numbers, certainly piqued my interest. You see, mathematics isn't just about numbers. It's also about recognizing patterns, making connections, and drawing conclusions from limited information. One of the powerful tools that we use for this purpose is inductive reasoning. Ooh, I can sense your confusion. Well, derived from observations and patterns, inductive reasoning allows us to make generalizations or conjectures. A conjecture is a conclusion made from observing data or an educated guess based on patterns. Dive in as we demystify inductive reasoning and its pivotal role in deciphering patterns. Speaking of deciphering patterns, we have a puzzle to decipher here. Take a look at these encircled numbers: 1, 4, 9, and 16. The next term is 25. It's essential to note that conclusions made from inductive reasoning might not always be accurate. They are educated guesses, and further evidence or counterexamples can refine or invalidate them. A sequence means an order in which one thing follows another succession. Each member or element is called a term. These terms can be written as a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, which means that a sub 1 is the first term, and so on. What I just showed you is an example of a finite sequence, meaning it contains a limited number of terms, where the end or the last term is identified. Other examples of a finite sequence include the stages of life and the first 30 natural numbers. On the other hand, an infinite sequence contains a countless number of terms, like the digits of pi and the list of negative integers. If I write all the positive perfect squares on a paper, it would take me forever. But we simplify this using an ellipsis, which are 3 dots at the end, implying that the sequence is infinite. At this juncture, let us get to the bottom line of our topic for today. A pattern in the sequence can be obtained, and the sequence can be written using a general term. Let us try finding several terms of a sequence given the general term. In the pattern, the number of times that 3 is added to 4 is less than the nth term, or n-1. Thus, let us equate a sub n and 3 plus 4 times the quantity of n-1. The second step is we will apply distributive property, that is, 3 plus 4n minus 4. Combining similar terms, we get 3 minus 4 equals negative 1. Bring down 4n, that is plus 4n. How about we do it the other way around? This time, I am going to show you several terms, and we are going to figure out the general term of the sequence, like in text. For the first example, we have 3, 7, 11, 15, 19. Again, the first step is to identify the pattern. Can you see the pattern in our sequence? Exactly. Notice that each term is 4 more than the previous term. 3 plus 4 is 7, plus 4, that's 11, and so on. We can search the pattern using a tabular form. As we close this chapter of our math journey, remember that patterns are everywhere, waiting to be discovered. They are like hidden treasures, and all it takes is a curious mind and a little math magic to reveal their meaning. Thank you for joining me on this journey of pattern generation. Until next time, keep exploring, keep discovering, and keep learning. This has been student teacher CJ on Equationators. What's up?